The Aquaponics Project at Sam Houston State University by Cody Handlin. A contemporary of Jacques Cousteau, the legendary ocean researcher Sylvia Earle, in an award-winning TED Talk, has the following startling quote. "In 50 years, we've taken, or we've eaten more than 90% of the big fish in the sea." An incredible statistic. In 50 years, 90% of the big fish in the sea. In his well-known book, Charles Clover, The End of the Line, takes this trend and extrapolates it into the year 2048, predicting that the remaining 10% of the big fish in the sea will face species collapse by the year 2048. As supplies from the ocean continue to dwindle, we rely on aquaculture production to make up for the soaring demand for seafood. In 1950, there were only approximately 1 million tons of aquaculture production. In 2006, 51 million tons, and in 2015, over 100 million tons, an exponential increase from 1 million tons in 1950 to today over 100 million tons. But not everyone agrees that increasing aquaculture production is sustainable at current levels. One of the problems in aquaculture production is a tremendous amount of fish waste. Many fish cannot be grown together in a small space without basically poisoning their own water with fish waste in the form of ammonia from their respiration and excretion. So the question is, where do we dump this water? Well, there's a solution that we don't have to dump this water in our rivers, lakes, and streams, causing potentially devastating ecological consequences. One of the things that we can do is we can turn this waste product into fertilizer. And that brings me to my research project, Aquaponics. Aquaponics is the combination of aquaculture together with hydroponics. Aquaculture is the raising of aquatic animals or aquatic plants for food, and hydroponics, which is pretty well known, is grown by supplying all the necessary nutrients in the plant's water supply. It's a soilless growing technique. So you combine aqua from aquaculture and hydro or ponics from hydroponics. And you put these two systems together in a recirculating system. One of the types of aquaponic systems, this is a common backyard system or small-scale system, is called the media-filled bed. And there's two kinds, simple flood and drain, which is also called ebb and flow. Here's a photo of a common type of media-filled bed system created from a stock tank. How does the system operate? The media-filled bed system is either continuous flow or ebb and flow, which means that the pump turns on, the bed floods, and then drains again. This is a photo which illustrates how one of these systems works. You'll see a pump. This is in the tank of the aquaculture. Also not in this photo, you'd have aeration as well. And at intervals, this pump turns on and pumps the fish water over a media. Again, it's not soil. Usually it's something like leca, which is lightweight expanded clay aggregate. That's what you see here in this photo. And then it drains back by gravity into the fish tank. This is a continuously recirculating system. Part of the research was to create a goal for our aquaponics system. I wanted it to be low cost, defined as costing under $500 for the first system. I wanted it to be modular. I wanted it to be off the shelf, and I define this as you could pick up 90% of the parts from your local big box store like Home Depot. I want it to be simple to construct with regular tools, and I wanted it to work or to be viable. This was originally an independent study as part of the Industrial Technology School It was to design, build, and test a working aquaponics system in the Sam Houston State University greenhouse. The first thing I did in this project was to design the media-filled beds. These were designed in a program called Google SketchUp, and this allowed me to visualize the design in 3 dimensions and to easily add dimensions to the project that could be viewed from all angles. This makes it also easy for a later person to come along and reconstruct the project or to add more beds. This is a design for 2 of the beds. We currently have 6 in operation with plans to expand to 12. This is just simply another angle from the front. This is an angle from the top, which shows the independently controlled valves that run to each one of the beds. And this is the system constructed in the greenhouse when it was first installed. You can see now the wood doesn't look as brand new as it did then. And also you see that we had a couple of beds that we didn't have in operation, but this is the pea gravel, which is our media. This is the very first salad that came out of the operation. Because I grew it myself, it tastes twice as good. These are the roots of the plants growing in our media, which is pea gravel. And this is one of the secret weapons of an aquaponics system, worms. How does fish waste turn into fertilizer? The first step is ammonia. Fish respire and excrete, and ammonia builds up in the tank. This ammonia is converted by nitrifying bacteria in the media-filled bed first to nitrites. Then, later, nitrites are still fish toxic and cannot be taken up by the plant, but these nitrites are converted eventually by nitrifying bacteria into nitrates. These nitrates can be taken up as nitrogen by the plant roots, and then the plant roots also filter, and then that water is returned to the fish tank. Again, this is a recirculating system which is continuously operating. These graphs represent the maturing or the cycling process of starting an aquaponics system. In the beginning, you'll have no native nitrifying bacteria, so you'll have high levels of ammonia, and as the bacterial colony becomes established, they'll begin to convert some of that ammonia into nitrites. And then finally, as the third stage, you'll see nitrates start to exist, and the nitrite levels will lower, and the nitrate levels will raise. Here's a way of looking at it. You have an ammonia spike, then you'll have a nitrite spike, and then lastly, you'll see nitrates being complete. And this is a cycling system. So in a mature system, you're going to see something slightly different. In a mature system, hopefully, you will see ammonia levels consistently low and nitrate levels consistently high. And this will indicate that you have a mature system. This represents the growth. Here's week 0 and week 3. A lot of growth in a short time. This is chard at week 0 and chard at week 3. This is basil or kale at week 0 and at week 3. This is tomatoes at week 0 and tomatoes at week 3. We brew peppers. These are bell peppers, week 0, week 3. And I think this is the most dramatic photo. This is week 0 and week 3. So you can see a lot of growth in a short period of time. Some of the things that have been grown in the system are eggplants, kale, green peppers, tomatoes, banana peppers. They grew really well in the system. In conclusion, I was able to build a system which was low cost, modular, and I was able to do it with the cooperation of a lot of helpful and knowledgeable professors like Keith Kugler or Mr. Kugler from the technology department and Mrs. Fry from the agricultural department and Dr. Tim Pancook and Dr. Lane also from the agricultural department. These photos have been used without permission, but I did find rather handsome and good-looking photos from each 4 of them, so I'm sure they won't mind. And thank you for staying to the end of my presentation. I hope you can visit Sam Houston State University and the Aquaponics project.